All right, today we're going to take a look at polar coordinates and conic sections, or conic sections in polar coordinates. So we've combined the idea of parametric equations with polar coordinates. Now we're going to take a look at some of these conic sections and write them in polar coordinate form. And then from last time, you can then envision it going back into parametric equations. So first, there's a definition for this E, which is not Euler's number, that 2.714. Instead, when you're dealing with polar coordinates and conic sections, this is referred to as the eccentricity. So it says F is some fixed point called a focus. We've dealt with focus points before. And then L is a fixed line called the directrix. We've dealt with that also. And E is some fixed positive number called the eccentricity. Then all the sets of points in a plane such that the distance from a point, any random point, to the focus and that random point, which may not be so random, to the line, if you take the ratio of that, that's called eccentricity. So when we first started talking about conic sections, we talked about this special focus in directrix by looking at the parabola. And we said if we have the same distance from any point to the focus and that same point to a line called the directrix, then those two distances would be equal. Then we have ourselves a parabola. So if you imagine taking a look at this definition for a parabola, the distance between that point and the focus and that point to the line is going to be exactly the same. So if you put a ratio, if you put them in a fraction, then you have the same distance over the same distance, and that's going to equal a 1. So a parabola, by definition of the parabola and by definition of this eccentricity, will always have eccentricity equal to 1. Yeah?
So for the formula, PF is that product, or that's the line segment?
That's the line segment. So that's the distance between the point P and the point F, and also the distance between the point P and the line. So whenever we're talking about a distance between a point and a line, we're talking about the shortest distance. Then when we introduced the ellipse, we didn't talk about the directrix. We mentioned the focus, but we didn't mention the directrix. But it turns out that an ellipse also has a directrix. So we know that there's a focus for an ellipse. So this is going to be closer to the focus point. So if you have an ellipse, we're looking at the points on your ellipse and the distances. So the distance from the focus to the point is your numerator. The distance between your point to the line is your denominator. And then it turns out that if you have an ellipse, that distance is going to be closer, the point is going to be closer to the focus. You'll have a smaller numerator than denominator, and that would make your eccentricity to be These notes will be online. These notes are being recorded, unless you have a specific question to ask me. We're defining an eccentricity. Eccentricity is the ratio between the distance from a point to a focus to a point to a line. That's PF and PL. And when we were studying parabolas, we define a parabola to have those distances to be equal. That's how a parabola was defined. And if PF and PL are both equal to each other for any point P that we choose, then this is going to be equal to 1. So, by this definition, the eccentricity for a parabola is equal to 1. For an ellipse, the eccentricity is going to be less than 1. Whether you get the picture or not, we can just wave that off and say, as long as we know, if we can identify the eccentricity and the eccentricity is less than 1, then we know that that's going to be an ellipse. Yes?
Is there something that is helping us choose the fixed, like why are we choosing that particular?
We're not choosing it. Sometimes we have to find it. Sometimes it's given to us. But we know if E is going to be equal to 1, we know it's a parabola. If E is going to be less than 1, we know it has to be a... Yes? There are, well, for ellipses, we know that we have 2 foci. But when we look at this from a polar coordinate point of view, we're just going to look at one focus point. In fact, that focus point, to make things easy for us, the focus point will be the origin.
Always?
Yes, for us. So it turns out that orbits of things like planets or satellites are actually defined by eccentricity. So we know how close they are to a circle versus getting a wider looking ellipse. This is still pretty hard to grasp. Is this still, are you guys starting to understand it a little bit? So this is just an introduction to the eccentricity, and the value of the eccentricity E tells us what kind of shape we would be looking at. And the next thing to do, the next step, is to actually see this in polar coordinate form. So let's take a look at the formula that they have in the book that shows you the polar coordinate form. And these snapshots are taken directly from your textbook. That the polar equation form is going to be given by one or the other sine or cosine, depending if it's opening sideways or upward or downward or whatever. the polar equation of the form r is equal to E, now E is eccentricity, times d, and d is the directrix. And we're assuming that this directrix is a y equals to some number or x equals to some number kind of directrix. It's a line that's either vertical or horizontal. It's not any sort of diagonal line or anything crazy like that. It's just going to be one of those two types of directrix possibilities. So we can put that into the equation as a constant. So E times D is a constant divided by 1, and then there's a plus and minus the eccentricity times either a sine or a cosine. Yeah?
Did we tell EL or is it different?
It's not really different. I think mathematically, I don't know if semantically is the word, but mathematically, L is the name of the line, and x equals d or y equals d. D is that constant, the number. So if you're okay with that idea, then you can call it L, but don't tell that to any other mathematicians. Yes?
Just out of curiosity, what would these equations look like if we had if it was functional words, just like in a general sense? Or
I'm not sure. So there's going to be some shift to it. So they might involve more sines and cosines. But I haven't really played around with that so much. When we make up our discussion board of notes, and if you come up with any more ideas like that, you can certainly post it up there. All right. Here's some examples of possible forms of the lines opening up either left or right or up or down, and your choice of positive or negative sines or cosines. And I think for simplicity's sake, if we're going to make up problems, I don't know what kind of problems that you'll have in your homework, but if I was going to make up a problem, I'll probably stick with this idea that your focus point is at the origin, your directrix would be on the left side, and then you'll have your parabola, ellipse, or hyperbola opening up to the right like this. So this, for me, would probably be the easiest type of equation to deal with. But, like I said, when you're doing homework problems, you got to be open to these other possibilities. So let's see if we can tackle a problem or two from your homework set. And this time I'm actually going to go into your homework set and try out some of these problems. One or two?
one.
One. All right. So this is asking us to write a polar coordinate equation of a conic with a focus at the origin and the given data. So the conic section that we want to draw is a parabola. That should automatically give us our eccentricity. And then the directrix is x equals to -2. And so that gives us another variable in our formula. Yes?
Sorry, I know I wasn't here Thursday. Why do we care about a conic section?
Why?
We're not trying to get a Conic section. It's called that because the Lapuz, parabolas, and hyperbolas are second unit sections of a plane skewed to a plane. So they're called.
We may also care for these types of things for the sake of being able to mimic the path of a of a moving body around an object, satellites and planets and stuff. And parabolas also help us focus light beams. So we're given two big clues that help us shape our equation. We're given our eccentricity for a parabola. We know that it's equal to 1 because it's a parabola. And our directrix is -2. So already we have our stuff set up for us. Now, we know that x is equal to -2 is a horizontal or vertical line? Vertical line. So we know that our parabola should be opening which way? To the right. Because the focus is inside of the parabola and the directrix is on the back. Yes? Only for the parabola.
How would you shift the, I'm sorry if I missed this, but how would you shift the polar coordinates? How would you shift the, if you wanted to shift the, if you had a curve set at the origin, you wanted to shift that entire curve somewhere in, how would you go about doing that?
I'm not sure how to shift the polar coordinate graph. Only way I can think about shifting it is changing it into parametric equations and then doing the shift in parametric equations. Because parametric equations, when you shift, you just add to the x and add to the y, and that brings you to a new point. So in polar coordinates, that seems to be a lot more difficult, actually, that idea of shifting. So. All right, well, based on our choices, I would probably choose the negative cosine one, right? I think the formula says something like we want our r to equal to e times d 1 minus e cosine theta. Like I said, the e's and d's are already figured out for us, so I think we just drop in those values, -2 over 1 minus cosine theta. And just for good measure, let's actually plot this and see if it'll work for us. Oh, we're going the other way. It has a negative, but it went out there. It should still be the same. And this is why we want to double check our work. See what happens if we put +2. Now it opens up the correct way. So, oh, they put the negative d here. They want the d to be positive. Yeah, so this x should equal to -d according to what they have. So our actual d is equal to +2. So when you're doing these things and choosing which of these formulas to use, it might be good to graph it to make sure that you get the correct answer. So it looks like it's a positive 2 that we want to put in, because our d is actually positive 2. Our Directrix equation says x equals negative d, and since this is negative 2, our d must equal a positive 2. So that should be our equation. Let's check. Oh, do we need an r equals? Okay, so that looks good. Any questions? I don't want to do all your homework, because then you guys won't have fun. You leave all the fun to me, and I don't want to have all the fun.
But the Directrix is shifting?
So why don't I start this and have you guys complete it. Write a polar equation for a conic with a focus at the origin with a given data. We have an ellipse, an eccentricity, and a vertex. And notice the vertex is 1 comma pi over 2. So given that kind of a point, I would have to assume that this vertex is actually written in polar coordinates. Where 1 comma 2 is actually where? So y equals 1. So that's actually your vertex.
So the earlier one had a Directrix that is shifting
The Directrix? Oh, the Directrix is a line. So if you graph that,
right.
you should see a line. So this is an ellipse, this is a vertex, and if this is the focus at the origin, right, then your ellipse should be opening up this way. So what do you need for an equation for something like this? It looks like we're going to need the sign opening up downward. I'm going to need a positive and then a sign for this one. So E is given. You have to find D. And remember that D is the Directrix. Where's the Directrix going to be for this case? Where? Y equals 3? How'd you get 3? The vertex is used to help you find the Directrix. Okay? Yeah? Because the focus is here. The focus is at the origin. This is one of the vertices. This is a focus. So if this is a vertex, it can't open up this way because you're not in the focus. All right, so remember that the eccentricity is equal to the distance between the point. In this case, we'll take that special point, the focus, divided by the distance between the point and the line. And you know that the eccentricity is equal to 0.5. And so from there, you should be able to figure out what this equation is. Somebody already said it. I don't know if it's right or not, but whatever. Okay? So that's how you can figure that out. And then from there, you can write your equation. And because this is an ellipse opening downward, you probably want to think about this as a 1 plus e sine theta in the denominator.
So the vertex is almost like a conic sector or the direction.
Yeah, the vertex, from the focus point, the vertex is going to be the straight line going to the directrix. Always, whether you're looking at a hyperbola, a parabola, or an ellipse. The only differences would be the distances from those points. Okay? All right, so like I said, you guys figure this out. Let's take another one, look at another one that gives you the equation, and then it's going to ask you to find some properties. Now, there's an equation that we already have been working with that we know, and so now we just need to kind of step back and find some properties about them. And problems number 4 and 5, I think, are very similar. So which one do you want to do, 4 or 5? 5? So here we have an equation. R is equal to 11 divided by 6 plus 6 cosine theta. And you notice, whoa, all those equations had a 1 plus or minus something in the denominator. So this one doesn't look, I mean, you could just graph it first and see what it's supposed to look like. But I think what you can do is try to massage this equation to make it look like, or to make it have a 1 in the denominator. How do you suppose we do that? Just pull a 6 out. Let's use a pull-out method. Uh-oh, what are you going to do with this 6? Well, just throw it up in the numerator, right? Does this give you a hint on what's happening? What do we have? Well, first, what's the eccentricity? So remember that the eccentricity it comes in 2 places. One of them is a coefficient of the sine or cosine. The other one would be up here somewhere, right? So because this is 1, then we know that 1 times anything is anything. Had this been something else, then you would have had to kind of break that. If this would have been a 5 or something, then you would have needed to have taken a 5 out of the 11/6 somehow. You guys can do that, right? You're math people. So now we've identified E, and also, because this is an easy one, because the eccentricity is 1, then D is going to be equal to this. All right, so pretty immediate that eccentricity is going to equal to 1, And because eccentricity is equal to 1, what's your conic section shape? It's a parabola. So the next thing it's going to ask is going to ask us to find the equation, the Cartesian equation of this thing, and then try to graph it. So let's see if we can find the Cartesian equation of this. So we have these two values so far. I could try to graph it and see how it's going to look like. Oh, if these equal 11.6, what's the directrix? X equals 11.6, y equals 11.6. So this is a 1 plus cosine. Which way is it opening? It looks like it might be opening to the left, right? And we said that this is a parabola, and this is written in polar form, so it looks like it's going to be a parabola centered at the, or not centered, but the focus at the origin, opening to the left. And so our directrix has to be expressed as what? X equals positive or negative? Positive 11.6. So this is a parabola. Eccentricity is equal to 1, which means the distance from the point, any point on the parabola to the line has to be equal to any point, that same point on the parabola to the focus. So the vertex is that nice point to look at. Should move my parabola a little bit. So what's the vertex going to equal? So we have a vertex at a specific point now. Yeah? Oh, yeah. This is 0, and this is 11.6. So now we have to think back of the formula for the parabola in polar coordinates. That's opening sideways. You remember? I don't. No, so that's the like the form using now let's go look at our notes. You know where to find your notes, right? And all the video recordings in case you missed a day or 5 days in class. So we started to talk about conic sections. And then it looks like opening sideways would look something like this. Y is equal to 4px, and P is the focus point. Oh, this is through the origin, but there's a shift. So we want to shift it. We do the H and K. So let's see if we could take this. This is the one opening upward. So opening sideways, we're going, what is it? What is it again? Y squared is equal to 4px. What was P? Was P the vertex or the focus? Oh, the origin. This isn't going to help us too much. I got the origin is 0. Is the shift going to help us? Focus is still what's the P? Yeah. It would have been. Oh, the directrix, so P negative P. Well, let's imagine that shift happening. P negative P. Y-intercept. Yeah. Maybe. Well, yeah, I guess when in doubt, go back to pre-calculus and try to figure out the intercepts, like Dave said. But let's see if we can, I don't know, should we try to punch through that? What do you think? Well, I think P could be 11 over 6. Because of the shift. Is that what you said?
Yeah, that's what I said, but
Adding another constant to p.
The point that we have right now is 11 12.
Well, that's the thing, is that our focus here is 0, 0. And so I haven't taken that shift into consideration. Let's see. I just said to give the equation.
Well, I just want to say equation, right?
Oh, the Directrix. Oh.
We already have that.
Oh, let's just answer it then. 1 parabola. What's this? X equals what? And then we know that it's a parabola opening up sideways, right? All right, so that looked like it was all good. Yeah, so I don't know if there's an easy or good way to find the equation in Cartesian coordinates like this, but normally you get all the information about the vertex, and then, so I guess if you really do want to find it, this suggestion was to find the intercepts, and then you can find, with 2 points, you can find the equation of a parabola. All right, maybe that should be extra credit. So if you want, find the equation of this. We didn't have a warm-up today, so as your extra credit, you can find the equation of this. Find the equation of this in Cartesian coordinates. All right. See you guys next time. Find the equation of this polar coordinate function. Writing Cartesian coordinates. What? Oh, so you're going to be note taker?
Oh, no, well, you said to about it in their class.
Yeah.
Yeah, I mean...
Did you come to me last time?
Yeah.
And said that you were going to be the note taker?
No.
You need a note taker.
But I can be the note taker. If you can't find anyone now.
But you're going to submit that to you?
Well, or for anyone who's also part of the...
Yeah, but you're the only one that's requesting it. That's kind of weird.
It happened before already. So.
Yeah, and you got paid for it?
Because there was no one else. It's like, it's very rare to find STEM students who...
Oh, there's a lot of STEM people that have nice notes. But they just want to step up.
No, but I'm saying
go ahead and email me, and I'll send your name to Max, and you guys can figure it out. Hi, Jasmine.
Is it supposed to look like this?
Which one? Is that the one we were doing? I need to stop recording.